See, today the questions will be on the optimization. Okay, so first question is, I think there is some noise coming from your end. Can you mute? Okay, yeah. The first question is, which step does Nesterov's accelerated gradient descent perform before finding the update size? Right. So, does anyone know like why the answer is this? Estimate the next position of the parameter. Okay. So, okay. So I think there is a lot of noise. You can mute yourself. Okay. So simple gradient descent algorithm is something like this. At time step t plus 1, your update is xt minus your step size times the gradient of the function. Okay, so but in Nesterov's accelerated gradient descent, um, so first you find the direction in which along which you need to move. So that is this thing. Okay. And now the you update your current position based on this direction. Let's say call this as YT. And then the next point is given by this thing. You apply gradient descent on YT. Alpha times the gradient of f evaluated at YT. Okay, so this is what, right? So now before you compute your update step, right, this thing, you first find the direction. Then you find the gradient descent along that direction from that point, actually. Right, so that's the thing. Estimate the next position of the parameters, and on that, the new parameters, evaluate your gradient descent step. Right, so select the parameter of vanilla gradient descent uh, that controls the step size in the direction of the gradient. So this is simply the learning rate, right? So evaluate the gradient at any point, and the learning rate decides how much distance you want to move in that direction. Okay. Any questions on this? So is the recording on? Okay. I think it's on. Now, what does the distance between two contour lines on a contour map represent? Um, so what is a contour map? Okay. So, share. So let's say f of x comma y square plus y square, right? Now, contour map is the level sets of this curve. Level sets of this curve means if x square plus y square is equal to if f of xy is 1, the set of all x and y that satisfies this. Now, if of xy is 2, set of all x comma y that satisfies this thing. So, in this example, this is how your level sets look like. Right? So, this is a circle of radius 1, that is first, and this will be a circle of radius 2. This is 1. This is actually square root of, right? And so on. So what does this represent, this circle and this circle? Right? Say they represent the rate at which the function is increasing. Okay. So I think that is what is the question. Right? What does the distance between two contour lines and a contour map represent? So this is the rate of change of the function. Is it clear? Okay. So moving on to the next question. Yeah, this is the same thing. Which of the following represents the contour plot of the function f of x comma y is x square minus y? I think there are some questions. Let's see. Um, yeah, like it is just the difference of two levels. Uh, that is true. Um, uh, but between the two contour lines, you have the distance also, right? Say, how should I put it? Okay, if this is uniform, let us say, right? So that gives the, I mean, in a sense, that gives you the rate. But if these are not uniform, yeah, it just describes the how much your function is changed between two level sets. Yeah, I mean the answer is a bit grayish there. You just need to pick the most appropriate one. Yeah. Um, yeah. So which of this represents the contour plot of the function x square minus y? Any guesses? Parabola, that is true. Uh, right. The parabola C is the right thing. Um, it is easy to see because you can see, right, y the level sets are y minus x square is f of xy. right? Say if f of xy is 0, you get your standard this thing. Okay, so now y is equal to x square plus 1. At x is equal to 0, this value is 1, right? So something like this, uh, right? The distance between any 2 points will be 1 in this two and this two. Okay, so that's how you have to find out the level sets, uh, right? Any guesses what can be the equation of f of xy for the last case? Circle? No, it's not circle. I mean, it you can see, right? It's if someone no, okay, it's not circle. It's ellipse. Someone asked for rate of change in the parabola one. What should be? See the see rate of change. You will be asked for any two level sets, right? So I don't think so. They just give you parabola and ask what is the rate of change. You should be given any two contours, and between them you might be asked. Okay. And what is the equation of this? The one I'm highlighting, the second. What is the guess of f of xy for this one? Right. So if here f of xy is it's not y is equal to x for sure, but it is linear for sure, or it is y is equal to x. No, because it's at x is equal to 0, it is not 0. Right. So it is something ax plus by. But these are parabolas are level sets of contour plots. Yes, yes, these parabolas are level sets of contour plots. The contour plot itself is the plot of your level sets of the function. Mhm. Okay. What is the main advantage of using ADAGRAD over the other optimization algorithm? Right. So this is, yeah, I mean, it is less sensitive to the choice of hyperparameters, and I mean, it should help converge faster as well, but I think this is the most appropriate one. Um, right. So, any questions on this? Okay. So, this is another question. When training a neural network using the straightforward gradient descent algorithm, uh, we observe a small change in the weights between two successive iterations. So, what can be the possible causes? Right. So, the eta is your learning rate, and it can be possible if eta is very, very small, or your gradient itself is very, very small. Okay. I mean, it is very easy to see. Right? If this is your typical gradient step, right? Xt plus 1 is xt minus beta times kgt. GT is your gradient. Now what they're asking is this thing xt plus 1 minus xt is very, very small. This is close to 0, right? So this is nothing but your minus eta times gt. Now this is possible if eta is very, very small or gt itself is very, very small. Okay. Um, Now you are given some data where we call X, right? Each row we call X where rows are data points and columns are features. Okay. And one column has most of its features as 0. Uh, what algorithm should we use here for faster convergence and achieve the optimal value of loss function? Right. So so this is the setting, right? So this is one example, one, and you have some say A1, A2, A3, A4, and so on. You have X2, they put some suffix here. So on. And so this is XM, right? And you have this thing. So what is being said is, so one of the columns has very, very small number of entries, that are 1, right? So in this case, which algorithm you should use for better convergence, right? So I mean, in general, uh, uh, so I mean, energy and momentum-based gradient descent are typically the same. I mean, it is also Nesterov's momentum. Typically, energy is called. Stochastic gradient descent is just your straightforward uh, this thing. So Adam is the uh, optimizer that combines both your momentum and the Adagrad style of your optimizer. So typically, Adam is the fastest. I mean, in in any given scenario, right? So yeah, I mean, given an option is, I mean, the Adam uh, should be the faster one to converge. I mean, almost all of them should converge to the optimal value given sufficient time and good enough learning rate, right? So yeah. So any questions on that? So basically, what happens is, let me some more detail. Uh, so if you are given something set of x and set y, and you want to fit your xw minus y, right? This is your loss function of w, right? And if I mean your training dynamics depends a lot on your this thing x transpose x, the matrix, right? So this is m cross d, and this is d cross 1, and this will be d cross d matrix. So if this is well conditioned, the condition is the condition number is nothing but your ratio of maximum to minimum singular values. It is well conditioned. I mean, typically any algorithm should work. I mean, if it is not, I mean, something like this, level sets are skewed, extremely skewed in one direction. Let's say something like this. Right? I mean, across this, your function changes a lot. Like in this direction, your function doesn't change a lot, right? So in this case, algorithms such as AdaGrad and all those things will help you out. Okay. Let's move on. So which is the what is the update rule for Adam? So as I said, Adam is the mix of both momentum and your AdaGrad style. Right? So AdaGrad style is something uh, which scales your gradient by the norm of the gradient, right? So that is square root of VT. And momentum is just the updated version of your gradient based on your history, past history of the gradient. Right, so this is the first is so it's a Adam is a combination of both. So that's why in general, in practice, it works well in variety of situations. Yeah. So what is the advantage of using mini batch gradient descent over batch gradient descent? That's one of the main advantage is the computation. The batch gradient descent is you compute the gradient by averaging all the data points in your data set. There's a full batch gradient descent. The mini batch samples some random points from your entire data set and computes the gradient on that. So that's why it is computationally much more efficient. And especially in deep learning, where the loss function is not convex. So by taking mini batch, it is like adding some noise to your gradient, right? And that has better properties of converging to a better minimum, right? So along with I mean, in general, you can option C is also somewhat correct. It gives a better solution. Mm, yeah. So which of the following is a variant of graded descent that uses an estimate of the next gradient to update the current position of the parameter? So any guesses on this? This is again the Nestorov's accelerated gradient descent. So remember, you move ahead and then compute the gradient, and then you make a gradient update step. Right? So that's the Nesterov accelerated gradient. So I think that is all I have for today. If you have any questions, I can clarify them. Let me stop recording. In this video, we will discuss the convergence of gradient descent rule for convex functions. The key assumption we make in this analysis is that gradients are bounded by a constant p, a positive constant p. When we say gradients are bounded, the norm of the gradients are bounded by p. And which also implies when the function is lipschiltz. So we want to optimize the function of x, which is convex, using the gradient descent updates. For the gradient descent updates, the next iterate is obtained from the current iterate by moving in the descent direction, which is the negative of the gradient. Eta determines the learning rate. And gt is the gradient of f of x at iterate t. So x, we assume x lies in d-dimensional space of reals, that is R bar d. And the gradient gt is denoted by and is defined by the gradient of f of x, where at x is equal to xt, that is the current iterate. So by assumption, we have the norm of gradient less than or equal to b, or b is positive. So the gradients are bounded above by a constant b for all. And we also assume that the function f of x is bounded below and it is greater than minus infinity. Otherwise, we cannot optimize these kinds of functions. So what does it mean is f of x is greater than or equal to f of x star for all x belongs to R bar D. This is an unconstrained optimization problem. So the search space is entire R bar D. And our goal is to go to x star as close to x star as possible. So we now analyze how the next iterate, that is xt plus 1, moves closer to the optimal x star from xt using the gradient descent updates. So we now analyze how xt plus 1, how close xt plus 1 gets to x star. In terms of its the previous iterate. Right, so simply by substituting the gradient descent update rule at xt plus 1, we obtain this equality. And just rearranging this, we get this second equality, that is xt minus x star minus eta times gt norm square. And simply expand this term, xt minus x star square plus eta square norm gt square minus 2 eta gt transpose xt minus x star. Right, so this is upper bounded by this quantity. First term is same and the last term is also the same, and the upper bound we use this fact. The norm gt is less than or equal to b, so norm gt square is less than or equal to b square. So eta square times gt square is less than eta square times b square. So call this inequality as A. As inside, it follows from norm gt less than or equal to b. So remember, we are analyzing only the convex functions. So the first order conditions for convexity, this should be greater than or equal to here. F of y, for any f, y and x in R bar D, we have this inequality for convex functions. That is f of y is greater than f of x plus gradient of f of x transpose times y minus x. Now substitute y is equal to x star here and x is equal to xt. What we end up getting is f of x star greater than f of xt plus gradient of f of xt transpose x star minus xt. Now remember, why we are doing all these things is we would like to upper bound this quantity. this quantity will be performed. So this can be rearranged and written something like this. The same thing. This quantity minus gt transpose xt minus x star is less than f of x star minus f of xt. And by using 2, we can substitute in a. This is a. And we end up getting norm of xt plus 1 minus x star square is less than equal to norm of xt minus x star whole square is eta square b square plus 2 eta times f of x star minus f of x. We have done nothing but just substituted this gt transpose xt minus x star with f of x star minus f of xt. Again, by pulling out this term to left and moving this term to right, what we end up getting is f of xt, f of x star is less than or equal to 1 over 2 eta. This 1 over 2 eta goes to this entire term. Xt minus x star whole square minus xt plus 1 minus x star whole square plus this is eta square b square. So we divide by 2 eta, we get eta b square by 2. And we would like to sum this above on t on both the left and right hand side. From t goes from 0 to t minus 1 and take the average. So by taking the average, we get t is equal to 0 to minus 1 f of xt, and if since the f of x star is constant, by doing the average, we get the same value. Remember, this is a telescopic sum. Only the first term of the first time 0, the second term in the last remains. Everything else gets telescopic terms. That is, everything else gets cancelled, and what we end up is the 2 terms, that is norm of x naught minus x square minus norm of xt minus x star plus eta by 2b square. Now, this is again upper bounded by r square by 2 eta t. R square is nothing but we define r as x naught minus x star. And because this is a positive quantity, then we are replacing this by something bigger because we are removing here this is a negative subtracting and we are removing that. So now we would like to make the right hand side as tight as possible. Hence, to make as tight as possible with respect to what r is not in our control, t is also can control, but t is something that cannot depend on this optimization. And b is also wrong. Something that we can control through the algorithm is the learning rate eta. So to minimize the right hand side, again, we differentiate with respect to eta and sub equal to 0 to find the optimal eta. So after differentiating, we get r square eta t plus d square by 2. 1 over eta is minus 1 square. And so the solvent for eta, we get r by capital B times the square root of capital T. So after substituting this eta into this equation, what we end up getting is b square root t r square times 2t. Then r b square divided by b square root t times t. So this is br square root of t, 2 times square root of t plus br divided by 2 square root of t, which is the same thing. We get br divided by square root of t. Now remember, minimum is less than average. And so minimum value of f of xt minus f of x star, we want to make it less than epsilon. That can be made if this boundary is made less than 20 epsilon 1. So what we end up getting is we need t to be more than v square divided by epsilon square to make the iterator of x t to f of x star epsilon close. That means if we need if p and r are unity and epsilon if my iterator of x t wants to be as close as to f of x star, that is the difference between them to be 0.001, I need 1 by 0.001 whole square iterations at least. So this is what is the convergence rate of the gradient descent algorithm when applied to your convex functions under the assumption that the functions are functions. When the function is assumed to be differentiable, that is non gradient of the function because there's no constant b for all x belongs to I by b. So under these settings, we obtain a convergence rate of 400%. And this can be improved if we make further assumptions on the kind of functions we are trying to optimize. Suppose f of x we want to optimize is smooth functions, that is it's bounded by a quadratic function. Then we can bring down this 1 over epsilon square with 1 over epsilon. If we even impose much stronger conditions on the functions, such as smooth functions and strongly convex functions as well, then we can further show that this the gradient descent update will have a quadratic convergence. That is, it converges at instead of O of 1 over epsilon square, we get log of 1 over epsilon. So to put in perspective, that is much faster than simple 1 over epsilon square. So this completes the analysis of the gradient descent update group in a convex setting when we assume the gradients are bounded by a constant.